Let's talk about the singleton. First, we will have a brief introduction to understand the main components of the pattern. Then, we will dive into code looking at two different implementations. The first version will be completely abstract and general, while the second one being a much more specific, real-world use case. After all of this, we will refactor our example implementation so that it would also work in a multi-threaded environment. Here I will also mention some special cases of the pattern which are really good to know about. In the fourth chapter, we will understand what makes the singleton such a controversial pattern and why does it face a lot of criticism. Finally, we will have a recap as looking at the pros and cons of the singleton, as well as its relationship with other patterns. The singleton is one of the simplest patterns out there, while also being one of the most controversial one. We will see the reasons for this later. It is one of the 10 creational design patterns, and note that it was also covered in the original Gang of 4 book. Essentially, the pattern ensures you that a class has only one instance, while also providing a global access point to this instance. These two features are going to be the key of the singleton. Now, looking at the UML diagram of patterns can help you see things from a different perspective. That being said, let's take a look at the UML diagram for the singleton. As you can see, it has only one main component, which is the singleton class itself. Other classes, such as the client, can interact with the singleton class only through the public getInstance method. By default, this method will be responsible for creating the instance, and by its nature, it must also return it. Let's see how the implementation of the general version looks like in Java. So as you can see, I created a new project, which is completely empty. Now, I will create a new class. Let's call it Singleton. Okay, so inside the class, we will have our private static singleton instance. Now, this is very important, right? That this field is private, because we want to prevent anyone outside the class from accessing the instance directly. We will also set our constructor to private, so that nobody can instantiate an object of this class from outside. And don't forget that we must also provide a global point of access. So for that, let's create a public static method, which will have a return type singleton, and let's call it getInstance. Now, these naming conventions are kind of a universal way of telling people that we are working with a singleton here. Okay, so inside the method, we will check whether the instance already exists or not. If it doesn't, we will create a new singleton and store it in our instance variable. And the method will always return the instance. Believe it or not, we are actually done, so let's test it. From the main method, we can print out the hash code associated with the instance. Let's do this printing multiple times so that we can compare the hash codes of the returned objects. You can see that we will always get the same object, which is exactly what we wanted to achieve. What we have just seen is very useful for understanding the pattern, but in a real-life scenario, the difficulty comes from knowing when to use the pattern and how to apply it. In reality, singletons are often used for managing and sharing global resources, such as a database connection, since you don't want to reopen the connection every time when you want to execute a new query. You could use it to have a configuration management system, where you store application settings and environment variables, or maybe you want to manage your own application-wide cache, where you can store and access frequently used assets. In a multi-threaded application, you might want to have a single instance of a thread pool to manage concurrent tasks efficiently. Or when you're dealing with some specific hardware resources, singleton is something you should at least consider. But another good example, which I want to explore a little bit more deeply, is logging. Since all objects that wish to log messages require a uniform point of access and conceptually write to a single source, it is a perfect example of when a singleton could be useful. Now you might be wondering, why are we using the singleton pattern here instead of a regular static class? There are multiple reasons for this. One of them is that we want to maintain instance-specific state in our singleton class. Static classes, however, cannot maintain state. You can also implement complex initialization logic in the singleton's constructor. to put them in contrast, static classes are usually used for libraries, extension functionalities, or just to group related utility methods together. Okay, so now let's see a simplified code for the logging example. So for this example, I already made a very simple logger class, and I will walk you through this first. Up top, we have our main directory, where we will put our logs, and some time and date formatting settings, which are all final, because there won't really be any reason for us to overwrite these later. Then we also have two public and two private methods. The two public methods can be invoked for the logging functionality. Here I only have debug logs and exception logs, but of course you could extend this to support as many types of logs as you want. Inside the public log debug, we will create the directory path for the debug logs. So for this, here I'm just concatenating the main directory path. Then I just get the current date and create the file name. I will also invoke the write method with the directory path, file name and message parameters. Now the message was also an input parameter for this method, so I'm just gonna pass that on. Now the other public method, the log exception, has a very similar structure. It's essentially the same, just with different names for the directory path and for the files. And here I will also invoke the write method, just as I did in the log debug. Now as for the write method, this is going to take care of actually writing the message to the file. First, it will create the folder if it doesn't exist yet. Then it will also format the message by invoking the getFormatted_message method. And inside the try-catch block, we will manage the output stream and do the writing. I also have this getFormatted_log message, which is gonna return the string I want to write into the files, based on the message of course. So to make it simple, I just added the time here before the message, and then also these dashes to separate the log messages from each other. Now in the main method, I instantiate our logger object, and I also do a debug log to make sure that it is working. Then I create an instance of the calculator class, which as you can see will do some calculations. Now again, to keep the example simple, this calculator is just a mockup class, but here you would have an actual calculator or any other class which wants to use the logging functionality at some point. In the doCalculations method, I want to log some messages like calculation started or calculation completed. And just for the sake of testing the exception logger, I will also invoke a division by zero exception. Now, the question is the following. How to get the reference to the logger? We have already created one in the main method, and we wouldn't even be thinking about creating another logger inside the calculator, right? Because that would mean every class which wants to log messages should create its own version of the logger, its own instance. This most probably would introduce some bugs or break the logger completely. Not to mention the overhead it creates. So one alternative we have is to create a reference to it. And we will set the value of the reference in the constructor. Now in the main method, we can just feed the reference to our logger when creating the object. This is a pattern called Dependency Injection. I will have a separate video about it, but to get the idea, the calculator class is using the logger, right? Because for the doCalculations method to execute properly, it wants to log some messages. So in other words, we can say that the calculator class is dependent on the logger class. In our case, we are injecting this dependency through the constructor, where it's clear and visible. Let's go ahead and test this. As you can see, the logs folder was created, and if I go inside, we have debug logs and exception logs. If I open these up, we see two debug messages, that the main is running and that the calculation has started. We don't see any calculations completed here. Now the reason for this is that if we go and check the exception logs, as you can see we had an arithmetic exception when we divided by 0. Okay, so now let's see another alternative to the previous solution. By the nature of the logger class, we can realize that it would make sense for us to have only one instance of it for the whole lifetime of the application. This should already remind us of the singleton. Let's see how to refactor the current implementation. Let's start with the logger class. First, I will create a private static logger field for the instance. Then I will also set the constructor to private. And finally, we need to provide a method for accessing logger functionality. So I defined the public getInstance method as we have seen previously. Now let's resolve the errors we have in the main class. We cannot create a logger instance here anymore, so just remove that line. And from now on, whenever we need to access the logger, we can just write logger.getInstance. We don't need to use dependency injection anymore, because inside the calculator, we can just get rid of the reference completely. And we can invoke logger functionality the same way we just did in the main class. Now if I go ahead and delete the previous log files, then run the application again, as you can see, everything works the same way as before. Be aware that the version of the pattern seen so far is for single-threaded applications. In a multi-threaded environment, however, it needs a bit of a special treatment to make sure that multiple threads won't create a singleton object several times. So why isn't the previous implementation thread safe? Let's take a look at the getInstance method again. And keep in mind that the instance is initially null. Let's consider the following scenario. Thread A enters the method and then the if statement. Then A gets descheduled, and let's say thread B is going to run. Now thread B also wants to use the singleton, so it will enter the method, then since it finds the instance null, it will also enter the if statement. It will create a singleton and return it. Now whenever thread A gets scheduled again, it will also create a singleton and return this different instance. Thus, we will end up with two different instances of the singleton class. Let's see how one can achieve thread safety by modifying the base implementation of the pattern. In total, there are many ways to achieve this. We will look at two of the most common ones. First, don't forget to mark the instance variable as volatile, to indicate that multiple threads may change it concurrently. As for the getInstance method, our initial idea could be to synchronize the whole method with the synchronized keyword. This approach would definitely work, but this creates additional overhead for the method every time it is called for the whole lifetime of the application, even after the instance has already been created and stored. But remember why the base implementation isn't thread safe. It's because of the if statement, right? So actually, we could just put the if statement in a synchronized block. It's important that for the monitor object here, we use a custom lock instead of writing singleton.class. Sadly, the overhead issue is still present. Now after the instance has been stored, it's unnecessary for the threads to wait in front of the synchronized block, so we could actually put another check before to see if it's even worth trying to enter the synchronized block. I understand this would look strange at first, but this way of double checking increases performance greatly as we avoid unnecessary overhead of the synchronized block. Talking about performance, there is another trick we can use to make the method faster. Since our instance is volatile, caching it in a local variable would also give us a performance boost. This way of achieving thread safety is called the double checking method. Now if you look at the getInstance method, you can see that by default, the singleton instance is only created when the method is called for the first time. So what we are doing here essentially is we are delaying the creation of the instance until it is really needed, which results in faster application startup, especially if the object would be computationally heavy to create. This is a technique called lazy initialization. Of course, if we want to enforce that the creation of the instance happens as early as possible, we can initialize our instance at declaration. In this case, we are using eager initialization. In Java, implementing singleton with eager initialization provides thread safety. Now it's important to mention that this technique only works because the Java virtual machine will make sure that the initialization of the static field happens on application startup, which means before invoking the main method. With that being said, you can see how providing thread safety might differ in other languages. In C#, for example, the virtual machine for the .NET framework, also known as the Common Language Runtime, flags every type with the before field init flag if it doesn't have a static constructor. For optimization purposes, the types flagged with before field init will be initialized only when they are accessed for the first time. So in C#, we would also need a static constructor to make sure that our singleton isn't flagged, so our instance is truly created using eager initialization. I will have a separate video about lazy and eager techniques, But to get the idea, there is always a trade-off. Assume that creating the singleton will take a long time. If you create it on startup, this delay will contribute to running the application. But after everything has been set up, there will be no delay when accessing the singleton for the first time. Or maybe your singleton serves a purpose and functionality which in some cases won't be used at all during application lifetime. In this case, it might be smarter to use the lazy technique as to avoid the unnecessary workload on startup. Now, as a special case, I wanted to mention subclassing the singleton. Some people would argue this breaks the pattern completely, but this isn't necessarily true. The Gang of 4 book does mention a couple solutions for it. The most feasible one involves creating a registry of singletons. But the question rises, is it really worth it? And the answer is, probably not. There could be some case where it's useful, but it's very rare, and even in that case, it's usually not the optimal solution. Also, as a side note, I just want to mention that inheritance is rarely the solution as opposed to object composition. So as a general rule, you should always prioritize object composition. You might have already noticed the resemblance of the pattern with global variables, as it introduces a global state into the application, often unnecessarily. For this reason, some people consider the singleton to be an anti-pattern. The global state leads to increasing tight coupling among your classes, with more objects becoming dependent on the singleton instance. Therefore, it requires analysis of implementation details to determine whether a dependency actually exists or not. Now, creating dependencies aren't always avoidable, but with the singleton, these dependencies are hidden in your code, instead of being visible and clear through interfaces. In many cases, it also makes unit testing much more difficult, as the singleton keeps its state for the whole lifetime of the application. So if we were to run several tests using the same instance every time, there would be conflicts, because the tests wouldn't be independent of each other. Remember that the independence of the tests is crucial when testing your application. Therefore, it is a very controversial pattern which needs to be used with awareness. For example, refactoring a class to be a singleton just because many objects need access to it is considered bad practice. In these scenarios, we could use dependency injection to feed the reference to the classes. Alternatively, if the dependencies become unmanageable, it could indicate that we should redesign the relation of those classes. Keep in mind that the singleton also violates one of the solid principles, which are intended to make object-oriented design more flexible and maintainable. Since the singleton has also the responsibility of controlling its own lifecycle, besides its specific primary function, it violates the single responsibility principle. Looking at the pros first, we have the following. We can be sure that the class has only a single instance, and we also gain a global access point to this instance. The cons we have just discussed. It violates the single responsibility principle as it is trying to solve two problems at once. With the tight coupling of the classes, it's much more difficult to unit test, and the pattern can mask for bad design as it creates hidden dependencies scattered in the project. We have the following relationships. A facade class can often be transformed into a singleton, since a single facade object is sufficient in most cases. Abstract factories, builders, and prototypes can all be implemented as singletons. The multithreaded pattern is a generalization of the singleton, since it allows you to create a fixed number of instances instead of restricting you to only one. Now, before we end, let's see a puzzle. Try to write down the steps for applying the singleton pattern to an existing class. Stop the video here to avoid spoiling the solution. The steps are the following. Identify the class that needs to have a single instance. Set its constructor to private. Declare the private static instance variable. Create a public static method for accessing the instance. And last, don't forget to ensure thread safety as we have seen. But before you do any of that, make sure that you really need to use the singleton, as it is one of the most inappropriately used and overused patterns.